Have you ever stopped to wonder what makes one app just fly, while another one just lags and sputters? Well, the secret isn't just about having a faster phone. It's a hidden language, an invisible architecture that organizes the absolute chaos of digital information. This is the world of data structures and algorithms, and today we're going to decode it. I mean, think about it. When you're dealing with billions, literally billions of pieces of data, from your social media feed to the entire global financial market, how you arrange all that information isn't just important, it's everything. And that's the big question, isn't it? How do we actually measure efficiency? That's what we're here to figure out. We're going to pull back the curtain on the principles that define speed in the software that, let's be honest, runs our entire world. So first things first, let's really get a handle on the problem we're trying to solve. The digital world is, by its very nature, incredibly chaotic, and that chaos creates some massive challenges. For example, your processor could be the fastest in the world, but it doesn't matter if the data it's working with is just a jumbled mess, right? Or how does a search engine sift through billions of websites to find the one you want in less than a second? How does your favorite online service not just crash and burn when thousands of people are all trying to log in at the exact same moment? Without a smart way to organize data, the whole system would just grind to a halt. Okay, so how do programmers bring order to all this madness? Well, they have a set of fundamental tools, a kind of secret weapon, known as data structures. Put simply, a data structure is just a specific way of arranging data so you can get to it and use it efficiently. You can think of it like choosing between a filing cabinet, a Rolodex, or a bookshelf. Each one is designed for a different kind of information, and picking the right one makes all the difference. Okay, now this might look a little intimidating, like something straight out of a textbook, but it's actually a fantastic roadmap for us. Let's break it down. You see at the top, we have data structure. It splits into two main families. Over on the left, we have primitive structures. These are your absolute basic building blocks. We're talking about a single number or a single letter. But the real power, the real magic, happens on the non-primitive side. This branches out again into linear structures, like an array, where data is just lined up one after another, and non-linear structures, like trees and graphs, which are perfect for mapping out complex relationships, like all your friends on a social network. Now, when you get right down to it, there are two main ways to actually store this stuff in memory. Sequential is like having houses all lined up in a neat row on a street. It's super easy to find house number 5, but man, trying to squeeze a new house in between 4 and 5, that's a huge pain. The other way, linked, is more like a scavenger hunt. Each house just tells you where the next one is hidden. This makes it really easy to add a new stop anywhere in the hunt, but if you want to find house number 5, you have to start at house 1 and follow all the clues. It's this classic trade-off between getting to your data fast and being able to change it easily. And believe me, this choice is at the heart of so many app design decisions. So, we've got our data all nice and organized. Great. But how do we actually do anything with it? Well, that's where algorithms come in. If data structures are the ingredients, algorithms are the recipe. You can just think of it as a step-by-step guide for getting something done. The key is that every single step has to be perfectly clear, there's a definite finish line, and the whole thing is designed to solve one specific problem, whether that's sorting a list of names or, as we see down here, finding the absolute shortest route on a map. And this right here, this sums it all up perfectly. A program isn't just one or the other. It's this incredibly close partnership between the data structure, the organization, and the algorithm, the action. You really can't have one without the other. They are the two halves that make all software possible. Which brings us to the heart of the matter. We've got all these different ways to organize data and all these different recipes to act on it, so how do we choose? How do we prove that one approach is actually better than another? I mean, we need some kind of objective scorecard, right? A mathematical way to predict how an approach will behave not just with 10 pieces of data, but with 10 million. And the answer is something called Big O notation. Now, don't let the name scare you. The idea is actually pretty simple. It's a grading system for algorithms. It tells you how much slower your program is going to get as you throw more and more data at it. And here's the crucial part. It always focuses on the worst case scenario. It's basically a guarantee that an algorithm's performance will never be worse than its Big O score. This graph explains it perfectly. See that wiggly line, the one labeled f of x? That's the actual runtime of our algorithm. You can see it goes up and down. But that smooth curve above it, the c times g of x, that's the Big O. It acts like a ceiling. As our amount of data grows, as we move to the right on the graph, We have a mathematical promise that our algorithm's runtime will never, ever cross above that ceiling. That's our worst case guarantee. Okay, let's bring this down to earth. On the left here, we've got a super simple search algorithm. It's just a loop that checks every single item in a list one by one. Now look at the analysis on the right. It's counting up every little step. But what really matters is the worst case. What if the thing we're looking for is at the very, very end of the list? Well, we have to go through all n items to find it. And that's why after you do all the math, its final score is just this, ON, or linear time. The time it takes grows in a straight line with the number of items. So, if big O is the ceiling, the absolute worst case, then it has an opposite. Big omega, which you see here, is the floor. It describes the best case scenario. For that same search algorithm we just saw, the best case is finding what you're looking for on the very first try. The performance literally can't get any better than that. So what's the bottom line here? All these notations give us a report card for our algorithms. And this table is basically your cheat sheet. Up at the top, you've got O of C, or constant time. That's the holy grail. It doesn't matter if you have 10 items or 10 billion, it always takes the same amount of time. Then way down at the bottom, you have O of 2 to the n, or exponential time. That's a complete disaster. An approach like this becomes impossibly slow with even a small increase in data. This is what developers fight to avoid at all costs. But here's the final, crucial piece of the puzzle. An algorithm's performance isn't always a single fixed score. The real world, well, it's a bit more nuanced than that. You really have to look at it from 3 different angles. There's the best case, which we measure with big omega. There's the worst case, which is our big O guarantee. And then there's maybe the most important one, the average case, what we can probably expect to happen on any given day with random normal data. Quicksort is the classic example of this. It's a super popular algorithm for sorting things because its average performance is a really good O of n log n. But, and this is a big but, in its worst case scenario, which can happen if you accidentally give it data that's already sorted, its performance completely tanks, slowing down to a crawl at O of n squared. In that right there, that's the whole game. There is no single best data structure or best algorithm for every situation. The real genius of software engineering is in understanding these trade-offs, knowing your data, knowing what you need to do with it, and then picking the perfect combination of tools for that very specific job. So the next time you use an app that feels incredibly fast, or one that makes you stare at a loading screen, you'll know why. It isn't magic. It's the result of countless tiny, invisible decisions, all part of this elegant dance between data structures and algorithms.